You are welcome, and it's a great pleasure to have you on this platform. This is star 121, Statistical Inference 1, and this is the second lecture. You will recall that in the first lecture, we discussed about sampling, and we highlighted the importance of sampling in statistics, as well as uh, some terminologies. We discussed some terminologies that are closely related to sampling, particularly concept of population parameters and sample statistics. We also discuss the number of sampling methods. Uh, the sampling methods were categorized into two: random sampling methods, which uh, ensure representativeness. In other words, those techniques allow ensure they ensure that each member of the population is given equal chance. The other category, non-random sampling methods, they don't give equal chance to units in the population. So for the random, we discuss simple random sampling, stratified sampling, cluster sampling, systematic sampling, multi-stage sampling, uh, and of course for the non-probability sampling methods, we discuss quota sampling, judgment, purposive, quota, and all of that. So that's the quick review of lecture 1. For this lecture, our focus will be on sampling distribution of a statistic, sampling distribution of a statistic. And at the end of the lecture, you should be able to understand the concept, basic concept surrounding the topic. Specifically, you should be able to define and explain the sampling distribution of a statistic. You should be able to differentiate between population distribution and a sampling distribution. The concept of sampling distribution leads to variability of sample or of a statistic. So we are going to explore variability. Precisely, we are going to understand how sample statistics vary across different samples. And we are going to understand the critical role that sample size plays in reducing variability. There are also few properties, one or two properties that we are going to uh, get used to in this lecture. One of them is the mean of sampling distribution, or maybe mean of sampling distribution of a given statistic, and the statistic could be mean or proportion. We are also going to look at a fundamental theorem, which is central limit theorem, and the importance of this theorem in statistical inference. At the end of the lecture also, you should be able to interpret standard error. You should be able to define it and distinguish it from standard deviation. You should also be able to calculate it for sample mean and for sample proportion. And the last objective is for you to be able to gain practical knowledge. So we are going to apply the concept of sampling distributions in constructing confidence interval. You will know the applications. We will not be able to really go deep into that, but in this lecture, you will know the application areas of the sampling distribution of the statistic, and then how, again, later, how you can use sampling distributions to perform hypothesis testing and compare statistics. So those are the key objectives. Now let's get to work. Let's start by looking at these two concepts, parameters and statistics. We mentioned them briefly in our first lecture. So again, because they are very fundamental, they are very crucial to our discussion today. So first, we will look at the definition. Parameter, I've told you, you can have this as a population, and from this population, you take a small sample. So this is population. This is sample. So a sample is a subset of the population. So any numerical value that is computed from the population, any numerical value computed from the population is what is called parameter. So if you compute total from the population, then we say population total. So it's a parameter. If you compute mean, average from the population, then you say population mean, and so on like that. Similarly, in the sample, whatever value you compute from the population, you can also compute it from the sample. So if it's coming from the sample, then you call it sample statistic. So for one, it is statistic, and for two or more, it is statistics. So therefore, statistics, they are estimates of the population values. I repeat that statistics which are computed from the sample, they represent estimates of the population values. So population values are parameters. Sample values are statistics. So in terms of the symbol, Greek letters are usually used as the symbol for population values. So like the population mean, you use the Greek letter mu. The corresponding estimate from the sample is called sample mean, and we use X bar. For variance, we use the Greek letter sigma square. So sigma square is the population variance. The corresponding value from the sample is this sample variance, and that is given as S squared. For standard deviation, as you know, is the square root of the variance. So it's called population standard deviation, and the symbol is sigma. Whereas for the sample, the corresponding estimate is denoted by S. So sample standard deviation. Another value that we can compute from the population is proportion. For proportion, we use P if the proportion is determined from the population. But if determined from the sample, then we use the P hat. The P hat. The P hat simply refers to hat there indicate estimate. So generally, population values are fixed and they are not usually known. Whereas sample values can vary from sample to sample, because if two of us are taking sample from the same population, your sample will be different from my own sample, may be different from my own sample, and therefore the estimate you will get from your own sample will be different or likely different from the estimate you will get from your own sample. So It's an important thing you need to know that population values are fixed and unknown in most cases, whereas sample values will vary. So it depends on this, on the sample. So one sample will estimate from one sample will be different from the estimate from another sample. So if, for instance, from this same population, we decide to pick another sample here, so we can call this sample 1, we call this sample 2. So the average from this sample, the sample mean here, which should be mean 1, sample mean 1. This one, sample mean 2, will be different. But there is only one fixed population value. So parameter values are fixed, but they are not known. So their estimates are obtained from the samples. So when we parameter values are there, they describe the population, whereas the sample statistics just describe the estimates from the sample. So that leads us to variability of a sample statistic. Earlier, I mentioned that if you take your own sample from the population from which I also draw my own sample, you get your own estimate, I get my own estimate, it will vary. So this is what we call the variability of the mean, for instance, the sample mean. So that's what we want to study. So the question is, by definition, what is variability of a sample statistic? So it simply refers to how the values of a sample statistic, which could be mean, which could be proportion, which could even be variance, which could be standard deviation. But our main concern for now will be the mean and the proportion. So we are looking at, this is a population, and from this population, different samples are drawn. So this may be one sample, this may be another sample, this may be another sample. Say sample 1, sample 2, sample 3. Several samples can be drawn from here. But each sample, let's say, will have a particular sample, maybe 2, maybe 3. So, but the same, we are drawing the same sample size from the population. So variability refers to how the values that we obtain from this sample, which is the sample statistic, how does it vary? How does it differ from one sample to another? So let's say our interest is the mean. That's the mean here, the mean here, the mean here. So we have the mean from sample 1, the mean from sample 2, the mean from sample 3. So variability of the sample mean is simply the understanding of how the means vary from sample to sample. So it simply refers to how that sample statistic differ across multiple random samples. All samples are drawn from the same population. So first thing that we must know is that different samples will produce different statistics because of randomness. So the mean from this sample will be different from the mean from this sample. They may be the same. No, at times they may be the same, but they will vary. If you have taken, for instance, all possible samples, so there will be those that will be the same. There will be so there will be variation across the samples. So there is bound to be variation, and the variation arises because of the randomness of the selection. So this variability forms the basis for the sampling distribution that we are talking about. Why is it important? We need to understand this variability to be able to quantify the uncertainty of the sample estimate that we have computed. So if we need to say with level of confidence the variability of the estimate, then we need to study sampling distribution of that estimate. And it also allows us to draw inference about the population parameter more accurately, because in most situations, as earlier mentioned, the population value is fixed and unknown. But we need to be able to say something about it despite it not being known. We need to be able to say something about it. So sampling distribution helps us to be able to say something about the population parameter that is fixed, that is unknown. So let's look at this example. Let's say a population is made up of these 4 values, maybe representing the amount of money in the pocket of 4 students. So there are 4 students in the class. The first person has, so that makes the class population to be 4. So there are just 4 of them in that class. The first person has 2 naira in the pocket. The second has 4 naira. The third 6 naira. The fourth 8 naira. So that represents the population. So we can say mu, which is the population mean, is the sum of all the money in the, in the in the pockets of the 4 students, and the sum divided by the number of students, that gives you 5. So the population mean here is 5. Now suppose you have to take sample. So let's take all possible samples of 2 students from this class. So somebody could take 2 and 4, that is 2 students, one having 2 amount of, maybe naira or dollar, but we have not put any currency now. So the other one has 4. So that's one possible samples: 2 4, 2 6, 2 8, 4 6, 4 8, 6 8. So if you notice here, you will know that these are all possible samples that can be drawn, provided we do not allow for replacement. So you can take 2 4, 2 6, 2 8. That is 2 4, 2 6, 2 8. Then you can also have 4 6, 4 8. Then you can also have 6 8. So these are all possible samples that can be drawn. How many possible samples in this case? So we have exactly 6. We have exactly 6 possible samples. So just as we computed the population mean, the population average, we can also compute the sample average for each of these samples. So here this sample average is 3, that's x bar 1. The sample average for this is x bar 2, which is 4. The sample average for this is x bar 3, which is 5. This is x bar 4, which is 5. This is x bar 5, which is 6. This is x bar 6, which is 7. So if you recall the statement we made earlier, we can see now that the sample values actually vary. They differ. The sample mean differ from sample to sample. The sample mean in sample 1 is 3. The sample mean in sample 2 is 4, and so on like that. The sample mean in sample 6 is 7. So This is what we call the variability of the sample mean. The variability of the sample mean. We are always interested in studying this variability. Very, very important. So we want to know the shape, we want to know the center, we want to know also the spread. So of course the spread is also the variability. So we are interested in one, the location. Two, we are interested in the spread. We are interested in the shape. So even as we look at this, we can see that the sample mean appears to center around 5, which happens to be the same thing as the population mean. We are still coming back to that. So we can now study the sample means. Can now make a general statement about this, the distribution of this sample means. So the distribution of this sample means is what we call the sampling distribution of the sample mean. So by definition, the sampling distribution of sample mean is nothing but the probability distribution of the sample mean across all possible samples. This distribution has two important properties that you must know. One property is that if we decide, and you can try that out, if you decide to find the mean of the sample means, the mean of the sample means, so that is, if you find the mean of all the 6 sample means that you have here, then it will give you the population mean. That property is the first one that is stated here. So the first one there, that is the mean of the sample means, is equals to the population mean. So you can refer to this simple symbol as the mean of sample means. The mean of sample means. So the mean, the average of all the sample means will give you the same thing as the population mean. That's what the first property there implies. And you must know that anytime, any day, anywhere. The second thing which I told you, we are interested in the location of that distribution. And that's what the mean there is trying to explain the location of that sample means. So the location is the mean of the sample means. Next is the spread or the variability. And what that implies is that this sample means, I can also find its variance. So I will call it sigma x bar, or sorry, sigma square x bar. That is the variance of the sample means. I can also find the standard deviation of the sample means. So that's what we call the standard error. So which means standard error is simply the standard deviation of the sampling distribution of a given statistic. So here, for the mean, the statistic of interest is the mean. So the standard error of the mean is the standard deviation of the sample means. Or put differently, it is the standard deviation of the sampling distribution of the sample mean. So that's the definition of standard error, and is different from standard deviation. So the standard error, one major result of one major property of the sampling distribution of the sample mean is that the standard error is equal to the population standard deviation divided by the square root of the sample size. So this is the result. So here now, to put it properly, the standard error, which we call the SE, the standard error, which we call the SE, is equals to the population standard deviation divided by the square root of n. N, don't forget, is the sample size. So in that example, the sample size is 2. The standard deviation will have to be obtained from here. We didn't compute it, but you can compute it, which means it is the standard deviation of this divided by the square root of how many samples are you taking each time, which is 2. So that's how standard error is computed. So these two properties are very, very important. They are very, very important. So we can easily visualize this property in histogram. This is the histogram of the of the example that we have. Of course, here you can see the mean of the sample means is equals to 5, as we have computed that, and the standard deviation of the sample means, which is the standard error, is equals to 1.41, and that is obtained by you computing the standard deviation of these sample means. So you can easily try that and you will get this result. So what are the factors that can affect variability? This is very, very important. Here we have one, the sample size is very important. It can affect the variability. If the sample size, which is small n, so big N is used to represent the population size. So for capital N, that refers to the population size. Small n, that refers to the sample size. So if the sample size is large, then the variability of the sample statistics will reduce. So larger sample size, in other words, the more samples you take, here in our demo, in our example, we took sample size of 2. If you increase it, that will shrink the variability of the sample mean. In other words, at the end of the day, the standard error will reduce. So again, remember the population standard deviation is also a measure of the population variability. So, and you know the standard error from here. The standard deviation, remember, is unknown, but let's say it's known. In our example, we can easily compute that population standard deviation, but it's fixed. So if that standard deviation varies widely, in other words, you have bigger variability in the population standard deviation, then of course your sample size, which is fixed, that will make the standard error to increase. So more variability in the population standard deviation will increase the standard error. So it is therefore very, very important that when you are taking your sample, you should ensure that your sample is random, is representative. If your sample is representative enough, then it will ensure unbiased estimate. In other words, it will ensure that the mean of the uh, sampling distribution of that statistic is equal to the population mean. That's when we will have an unbiased estimate. Precisely when the mean of sample means is equals to the population mean, then you have unbiased, an unbiased estimate. So I repeat, when the mean of the sample means is equal to the population mean, then you have an unbiased estimate. So to have an unbiased estimate, it is very important that your sample is random, that you use random probability, sampling method. So variability decreases as sample size increases, because if you look at the expression for standard error, so the standard deviation is fixed, but if you take more and more samples, and if the sample size is big, then your standard error will decrease. So which means variability decreases as sample size increases. So we are always interested in small variability. So small variability in your standard error actually implies that you have a more reliable statistic. Take note of that the smaller your standard error is, the more reliable your estimate. So let's perform an experiment just to look at how these properties, how they behave. So in this experiment, we want to simulate variability of a sample statistic. So the first step is that we will generate a population of 100 individuals. 100 individuals, such that the mean and the standard deviation, okay, we are generating population of 100 individuals. So we are actually generating the age of those individuals. So, and we want the average age, which is now going to be the population. So which means our population is made up of 100 individuals, but the mean age is 50 and the standard deviation is 10. And from these 100 individuals, we will first of all take a sample of 5. So we take a sample of 5 and take all possible, as many samples, so to say, as many samples of size 5 as possible. Then we move to take as many samples of size 10 as possible. And then we move to take as many samples of size 20 as possible. So we have sample size 5, 10, 20. Then we will compute the sample means for each of them and also compute the variability for each of them. Remember, to compute variability, we use the standard error, which is the standard deviation divided by the square root of the sample size. Then we will plot the distribution of the sample means for each sample. So this is the simulated population, the simulated ages of the 100 people, that constitute the population. So we have the first person 44.3, 47, and so on like that. So this is the population value. And then this is the histogram of that population. As you have been told, here is the center, which represents the mean of the population. So you can see you are already familiar with this kind of shape. This is a normal shape. So in the normal shape, you have equal spread around the center. So the standard deviation of the population is 10. So for the first sample, when sample size is 5, and then all possible samples of size 5 were drawn from that population of 100. So we plot the means, the sample means of all the possible samples. That's what you have here. That's the graph. And then what we notice for this, when the sample size is 5, is that the mean of the sample means is 50.79, which is slightly above the population mean, but certainly not too far. The standard deviation is 4.14535. Again, when the sample size is 10, what can we notice? We notice here that, again, the mean of the sample means, that's what you have here, is also around 50. It's around 50. And then the standard deviation has come down, has reduced to 2.89. And you can see the effect of the sample size. So increasing the sample size from 5 to 10 has led to the standard deviation of the sample means being reduced from 4.14 to 2.89. And when the sample size increased to 20, of course, the center still remain around 50.9. So, which means it's still unbiased. Still unbiased. So, the standard deviation of the sample means has also reduced. So, this is the standard error. This is the SE when n equals to 20. This is the SE when n equals to 10. This is the SE when n equals to 5. So what we are trying to say here is that as the sample size increases, this expression, which is the standard error, will be affected. As the sample size increases from 5 to 10 to 20, the standard error, don't forget, the standard error is the standard deviation of the sample means. The standard deviation of the sample means. That is the standard deviation of the means of all possible samples of a given size. So that measure, standard error, is a measure of variability. And you can easily see when the sample size is 5, you can see the shape where the center is located. When the sample size is when the sample size is 10, you can see the shift. I mean the shape, and when the sample size is 20, you can also see the shape. So, but before I leave this place, remember that the shape of the parent, the original data, that is, the shape of the original data, as you see, is normal. The shape of the original data, that is the population itself, is drawn from a normal population. It has a normal shape. That's a normal shape. Can you also look at the shape of all the possible samples? If you look at the shape of all possible samples, they are also normal. They are also normal. You have been taught a normal distribution in your descriptive statistics. So it's a bell shape and is symmetrical and so on and so forth. So you can see uh, the shape is normal. But suppose the shape is the shape of the parent population is not normal, which can happen. Maybe it's skewed. Maybe it has something like this. It's skewed. Or maybe the shape is skewed to the right or skewed to the left. So, which is not normal. What do we do? Or what will happen? So we are going to talk about that. So, but before we talk about that, let's summarize what we have uh, discussed so far. One, when we talk about variability of sample statistics, we are talking about the sampling distributions and how these sample statistics vary from sample to sample. Again, we have also noticed that this variability, the spread of the sample statistic or the sampling distribution uh, of the statistic will be affected. Precisely, the variability, which is measured in terms of the standard error, decreases as more samples are taken. So variability decreases as sample size increases. In, therefore, thus ensuring estimate improvement in estimate reliability. So we are doing all of this because we are preparing ground to how we can use this knowledge to construct confidence intervals and perform hypothesis testing. So two, or rather now three takeaways. Three takeaways. When we talk about sampling distributions, we are simply concerned about how sample statistics changes from samples to sample, so people can go to the same population, draw their sample, or you can draw several samples from a population. Then the statistic that you compute from that sample will change, will differ from sample to sample. That's something you should never forget. Next is that if you take more and more sample, if you increase the sample size, then you are reducing the variability of the the standard error. You are reducing the standard error of that statistics. In other words, you are reducing the variability of the sample statistics. So we've talked about this sampling distribution of the sample mean. So those are things we talk about, and the key properties. But I'm now going to emphasize on the shape. I've talked about it briefly. So the shape, we have seen the center is always the center of the sample mean is always the same as the population mean. In other words, the average, the arithmetic average of the sample means is always the same thing as the population mean. That's what this is saying. The standard error will always depend on the sample size because of the expression which says standard error, as you can see in that formula, is the population divided by the square root of the sample size. So now let's look at the issue of shape, and that leads to the theorem that I earlier mentioned, which is called the central limit theorem. It's a powerful theorem in statistical inference. And we are just giving the basic application here. And what does this theorem say? What does it say? It says that if your sample, for large sample sizes, the sampling distribution of the sample mean becomes approximately normal, regardless of the population distribution. Earlier, I mentioned that this is the population distribution. That is the parent population. The parent population, as you can see, has a normal shape. That's a bell shape. A normal shape, no, that's a bell shape and it's symmetrical. So if the parent population is normal, so if the parent population is normal, there is no problem. You are likely, of course, the sampling distribution of the sample means will be normal. This sampling distribution of the sample mean will be normal. But this theorem now is saying even if the parent population is not normal, if the shape is not symmetrical, regardless of the population distribution, could be any other distribution. There are many distributions, gamma, whatever. So it doesn't matter what the parent population is. The shape of the sampling distribution of the sample mean will be approximately normal. So that's what the theorem is all about. So if you have the parent, that is the population, let me use population instead of parent. Or let's continue. So if this is parent, and then this is the shape of the parent, then what is the shape of the sampling distribution of the sample mean. So if the parent is normal, then without any serious trouble, the shape of the sampling distribution of the sample mean will also be normal. But regardless, that's what the central limit now is saying. If the shape of the parent is anything, even if the shape of the parent is anything, then the shape of the sampling distribution of the sample mean will be normal. So when I write n here, I mean normal. So don't forget this important theorem. And it has two key uh, significance. One, it facilitates hypothesis testing and confidence interval. When we get there, we will expatiate. So it allows us to test hypothesis. And two, it also helps us to watch out for the sample size. So watch out for the sample size. Remember, the condition for this theorem to hold is that the sample size must be large. The sample size must be large. So there's a big something here which determines this. That is the sample size. That is the sample size. The sample size must be large. So the question usually is, how large is large? So this thing will be true. In statistics, sample size above 30 is considered to be large. So this theorem will hold if the sample size is greater than 30. So which means if you want your estimate to the sampling distribution of the sample mean to be approximately normal, then you need a sample size that is above 30. If the shape of the original or the parent population is not known or is not normal. So if the parent population is normal, but you don't have enough sample size, there is no cause for alarm. The sampling distribution of the sample mean will still be normal. But if the shape of the parent population is not normal, then you need large sample. You need large sample. That is sample size greater than 30 for you or for the sampling distribution of the sample mean to be approximately normal. So this approximation, this is what we call normal approximation. So, and is used in many statistical tests. So we've talked about this. We've talked about measure of the variability of sampling statistics. We have also talked about the mean of the sample mean. Sorry, um, the mean, the standard error, which is the standard deviation of the sample means. That is, the standard error. We've talked about that. Suppose we are dealing with proportion. We've not talked about. So for proportion, let me talk about uh, 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 proportion. For you to talk about mean, like in our example, you are looking at the age. So mean is computed from quantitative variable. So any variable that is measured, or any quantitative variable like age, score, and so on, you can talk about the mean. Price, income, and so on, you can talk about the mean. But marital status, for instance, we can't be talking about the mean. So we can only talk about any variable that is in category. Then we might talk about proportion. So gender, for instance, we can talk about the proportion of female in the class, the proportion of male in the class, and so on, like that. So the measure of the proportion from the population is given as the capital P. So capital P will be capital, uh, whatever you are, whatever characteristics you are trying to measure. Sorry, whatever characteristics you are trying to measure, uh, which means you can't. So it will be count of um, of successes in the population over the number of uh, items in the population. So if in a class you have 10 students in the class and 4 are females, then the proportion of females will be 4/10. So proportion is the number of successes over the uh, population size. So if you take sample also, so it will be number of successes. In other words, number of cases with the attribute of interest over the population size. So this expression measures the standard error for the proportion. So the standard error for proportion is the uh, the number, the proportion of successes times 1 minus p, which is the proportion of failures. So p here refers to proportion of successes, that is proportion of successes. Then 1 minus p is the proportion of failures. So, and then the product divided by n, that gives you the standard error for the proportion. So the first one there is the standard error for the mean, and the second is the standard error for proportion. Don't forget. So if we are dealing with quantitative variables, then we 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 can compute the mean from there. If we are dealing with variables, the categorical variables, then you can compute or obtain proportion from there. So regard whether for mean or for proportion, the property still remains that smaller standard error indicates that you have more precise estimate, and standard error decreases as sample size increases. Whether standard error from the mean or standard error from the proportion. So to summarize the properties of the sampling distribution, for the mean, the center is equals to the population mean. Don't forget that. The spread, which is determined by the standard error, decreases with large sample size. So as you increase the sample size, then of course your uh, your standard error, you know, decreases. So it's always advised, it's always advisable that you take larger sample sizes where possible. There are situations where it may be expensive, to take uh, larger sample sizes. And then in terms of the shape, we have applied the central limit theory, that the shape of the sampling distribution is approximately normal if the sample size is large enough, regardless of the shape of the parent population. So those are the properties for the sample mean. The same thing for the sample proportion. The mean of the mean of the sampling distribution of the sample proportion is equal to the population proportion. So in that case, we say it's unbiased. And the spread or the variability is measured as the square root of the product of the proportion of successes and the failure divided by the sample size. That's what you have here. And the last property is about the shape. The condition for the shape to be normal is that, one, you have large samples when the product of the sample size and the proportion of successes is greater than 5. And at the same time, the product of the sample size and the proportion of failure is greater than 5. So that requirement is very important. So it's remember the condition for the sample mean is for the for you to have large sample. Yes, for proportion, you still need large samples, but only when the products of the sample size and the proportion of success is greater than 5. So the effect of population distribution is one, in terms of the normal population, and I've said it before, if the population distribution is normal, then the sampling distribution will also be normal, even if the sample size is small. Even if the sample size is small, so it will be normal as long as the population distribution is normal. But if the population distribution is not normal, then under the central limit theorem, you need a large sample for the sampling distribution to be approximately normal. If the sample size is small, then the sampling distribution will just mirror the shape of the parent population. So this must be very clear to you. So if you look at the shape of the sampling distribution of any statistic and it's not normal, then it's probably giving you the mirror of the population distribution. So we can also talk about the sampling distribution of difference between two means. Sometimes you have two populations. You can have population 1, you have population 2. So we are trying to look at the difference between two populations. So if we are looking at difference between two populations, then we have to take sample also, uh, from each of the populations. So there will be sample from population 1, sample from population 2. And then on that basis, we can determine the distribution of the difference between the sample means of the two populations. So the result, this is just summary of the results. So the difference is just going to give you for the mean, that is the location of the difference. You can easily get it by finding the difference between the two population means. The difference between the two population means will give you the mean of the sampling distribution of the difference of two population means. The standard error is what you have there, the square root. You remember what you have inside is the population variance for the first population over the sample drawn from the first population, the sample size from the first population, plus the standard deviation, the variance from the second population divided by the sample size of the size of the sample drawn from the second population. So we need this as a basis for comparing, our testing hypothesis about two groups. We can have in experimental design, you can have two groups, and then you are comparing the average of the two groups. For instance, this your class is a group different from the last year class. So I can compare performance of last year uh, uh, student with this year. So we have two groups. So this kind of uh, uh, this tool can be used to compare and even test hypotheses about uh, two groups. So this practical example, you have to do it on your own, just as you know, something similar to what I did. So do your own. Assuming you have population that consists of 0, 2, 4, 6, then first of all compute the population mean of each of them, the population mean of the values, the standard deviation of the values. Then from this, generate all possible samples of size 2, which could be 02, 04, 06, 24, 26, 46. So you can write out code to do the simulation for you, or you can also try with your hand. Then for each sample of size 2, calculate the mean, and then calculate all the sample means, then plot the distribution, and then write your observation regarding the variability of the sample mean. So you can visualize that, and then you can also repeat the experiment over and over again. You can increase the sample size and see how the shape behave. So this is the summary of our discussion so far. So we've talked about the sampling distribution. We started with the variability of sampling uh, distribution, and so variability of sample statistics, and we have seen central limit theorem, how it ensures normality for large samples. We have also discussed extensively standard error measures, uh, uh, how it is used to measure reliability or precision of a sample statistic. And we have seen that uh, this sampling distribution of a statistic has a lot of applications uh, in statistics, particularly for confidence intervals, hypothesis testing, and for comparing groups. So before we close for this, uh, we have multiple choice questions for you. So uh, maybe you respond on you can respond on the review, uh, the review uh, side of the YouTube, if possible. So just type the question number, and your option. Type the question number. So this multiple choice question will help us to see how much of this lecture we are able to grasp. So this is the first question. What is the primary purpose of a sampling distribution in statistics? That's question one. What is the primary purpose of a sampling distribution in statistics? A, to describe individual data points. B, to understand how sample statistics vary across samples. C, to determine population parameters exactly. D, to avoid sampling errors. I don't know if I'm able to see your, I don't know if I'm able to see your, yeah, some people are really doing, yeah, some people are doing well. Yeah, that's good. I can see Master Martins, Dada. Yeah, that's good. I think you guys are building consensus around B. Uh, you are building consensus around B. Okay, so let's, because of time, let's see the answer. The answer in this case is B. So if you if you have chosen B, clap for yourself. So let's move to the next question. We have about 10 questions. What does the central limit theorem state about the sampling distribution of the sample mean? What does the central limit theorem state about the sampling distribution of the sample mean? It is always uniform regardless of sample size. It approximates a normal distribution as sample size increases. It is identical to the population distribution. It becomes more reliable as the sample size increases. What are your, yeah, number two, number two, number two, yeah, some people, again, people are building consensus around B. Because of time, I think, because of time, let's go to, what is the answer? The answer is B. So you are correct. People seem to be, the class is brilliant, very brilliant students. This is question number three. How does increasing the sample size affect standard error? How does it? Does it increase standard error, or does it decrease standard error? A, increases the standard error. B, decreases the standard error. Has no effect on the standard error. Makes the standard error infinite. Wow. Only a brilliant person will get this. Good, good. Dada, Mubarak. You guys are doing fine. So what's the solution? People really listen very well. This is uh, a very, very brilliant set of people. So correct answer is B. Let's look at this. What is the formula for the standard error of the sample mean? What is the formula for the standard error of the sample mean? Even closing your eyes, you could easily pick the right answer here. I know because some people have been selecting certain option they think that will also continue. Uh, Let me see what you are selecting. Yeah, yeah, Tobilola, you are doing wow, wow, wow. Okay, so that's good. The correct answer, the correct answer is C. The correct answer is C. Now, next question. In a sampling distribution, what does the standard error, what does it represent? In a sampling distribution, what does the standard error represent? The average of the population, the variability of sample means across samples, the total population variability, the range of the sample data, the total population variability, the range of the sample data. What are the options? What are the options? Yeah, I can see people selecting B, B, B. What does standard error represent? Somebody is typing that question for me again. What does standard? Okay, thank you for selecting. Thank you. Okay, so that's great. That's great. That's great. That's great. That's great. What is the correct answer? The correct answer is B. The correct answer is B. The next question, I think question 6 now or so. When is the sampling distribution of the sample proportion approximately normal according to the central limit theory? When is the sampling distribution of the sample proportion approximately normal? When the population is uniform, that's A. B, when the product of the sample size and the proportion of sources is greater or equals to 5, and the proportion of the product of the sample size and uh, the proportion of failure is greater or equal to 5, when n is equals to 10, when the proportion equals 1. What are we saying? What are we saying? What are we saying? 6. Some people are brilliant. Some people are brilliant. Some people are brilliant. Some people are brilliant. That's great. So let's look at the correct answer. The correct answer is B. All right. So B says when the product of sample size and the proportion of sources is greater or equals to 5, and at the same time the product of the sample size and the proportion of failure is greater or equals to 5. Now the next question, I think question 7 now. What happens to the shape of the sampling distribution as the sample size increases? What happens to the shape of the sampling distribution as the sample size increases? A, it becomes skewed. B, it approaches normality. C, it remains constant. D, it becomes undefined. Yeah. What are you? What are your choices? What are your choices? Excellent. Wow, 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 wow. People are doing fine. People are doing fine. Okay. Let's see the answer. The answer is B. Clap for yourself. Now, something, no, for you to calculate. Something for you to calculate. If the population standard deviation is 10 and the sample size is 25, what is the standard error of the sample mean? What is the standard error of the sample mean? A 0.4, B 2, C 5, D 10. Something for you to calculate. Wow. Wow, 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 wow. Great. So let's look at the answer. Let's look at the answer. Yes, this is the answer. B, and that's the explanation. So standard error is equals to the population standard deviation over the square root of n, which is simply 10 over the square root of 25. Square root of 25 is 5. So 10 divided by 5 is equals to 2. Next question. What is the primary purpose of increasing the sample size in an experiment? Why must why will you want to increase the sample size in an experiment? A, to increase the population mean. B, to reduce variability in the sample statistic. C, to increase the sampling error. D, to avoid random sampling. What are your options? What are your options? Ah, yeah. Wuraola did not put the option there. Simply put 9. Okay, you have done that now. Okay, so I'm happy you are getting these things. So to reduce variability is actually to improve the precision of your estimate. So uh, taking more sample, helps you to achieve that. The correct answer is B. Finally, why does the standard error decrease as the sample size increases? Why does the standard error decreases, or why does the standard error decrease as the sample size increases? A, larger samples are less random. B, variability among sample means reduces with more data points. C, larger samples have higher variability. D, population size affects standard error. What are your options? That is the last question for the day. That's the last question for the day. Abraham Bankole, you chose A. Martins, you chose 10. Yeah, it is not true that larger samples are less random. It is not true. Those choosing A, you are probably going to miss it. So let's know the true answer now. The correct answer is B. So, ladies and gentlemen, this is the end of. There is one question I think we must have answered it. Uh, wow, I don't know. I can't see the question again from here. Can't see the. I think we must have answered it. So, if you enjoyed the class, then just type yes, and otherwise type no, and then we continue our discussion on the WhatsApp group. If you have not subscribed, make sure you subscribe to this channel, and then I hope to see you again next week. Bye.